Okay, everybody, this is the part two of the lecture that we had on Wednesday. This is the stuff that we didn't have time to get to in lecture. So you need to view this uh, before class on Friday, if at all possible. And so we had talked about the idea that we have a secondary alkyl halide, which can do both SN1 and SN2 chemistry. And if we subject this particular molecule, where the bromine and the methyl group are cis to one another, to a strong nucleophile, we had predicted that this would be, because we got a strong nucleophile, that this would prefer the SN2 reaction, and we would invert the stereochemistry at this carbon atom right here. But if we use a weak nucleophile like water, we would end up with a mixture of products, because this would have to undergo an SN1 reaction where the leaving group has to leave first, and then the oxygen atom of the water could then attack either from the front face or the back face, if you will, of the carbocation and give a mixture of products, both leading to an alcohol, but different products. And so we had predicted that that would be the case. And in fact, when you run the reaction, what you find is exactly that. So in the case where we're using a strong nucleophile, the nucleophile does approach from the back side and kicks out the leaving group, and you end up with inversion of stereochemistry at this particular carbon atom. And so you go from a cis relationship of the two substituents on the cyclohexane ring to a trans, and it's 100%. You get only the trans 4-methylcyclohexanol out of this particular reaction. However, when you use the weak nucleophile, water is just not a strong enough nucleophile to come in and displace the bromide in an SN2 reaction. And so the only way water is going to behave as a nucleophile is if the leaving group leaves first. And so the leaving group leaves, the bromide leaves, you end up with a secondary carbocation, which is, it's okay. It's not the most stable, but it's all right. This, of course, is planar, and water can either approach from the top or the above face, as they call it here, and you end up with a situation where the oxygen atom and the methyl group are cis to one another, or it can approach from behind or below, as they mention it here, and you end up with the trans isomer of the alcohol. Now, these are intermediates. These are called protonated alcohols. If you'll notice, we have the carbon-oxygen bond that we need, but we have one too many hydrogens, and oxygen here has a formal positive charge. And so what happens is that the bromide anion from the leaving group comes in and abstracts the hydrogen. It functions as a Lewis base here, picks up the proton. These oxygen hydrogen electrons go onto the oxygen. You end up with the alcohol plus HBr, hydrogen bromide, as the byproduct. And so this is going to be very important in the demonstration that I'm going to do tomorrow. So don't forget to bring your devices that can record video for that. Okay, so if we think about it, the better the leaving group, the faster the reaction. So leaving groups increase as you go down a family, and they improve as you go from left to right in a periodic table. So as you go down a family, for example, if we're talking about the halogens, the alkyl halides, iodide is going to be a better leaving group than bromide, is going to be a better leaving group than chloride, and fluoride is actually a horrible leaving group under most conditions. And so, however, that doesn't tell us whether or not we're going to have an SN1 or an SN2, because it turns out that better leaving groups favor both SN1 and SN2. You know, if you want a really quick SN2 reaction, you need to use an alkyl iodide. If you want a really fast SN1 reaction, you need to use an alkyl iodide. So better leaving group, the better that these reactions actually occur. The nature of the solvent is another factor. So leaving group matters, solvent matters. We know that polar protic solvents like water and alcohol will favor the SN1 reactions, because those ionic intermediates that we generate, we're going to be stabilized by the solvation that those polar protic solvents can provide, and so that lowers the energy of activation. It turns out that polar aprotic solvents, however, favor the SN2 reaction, because the nucleophiles won't be solvated. They won't have that solvent shell around them, and therefore they're more naked, as we talked about on Wednesday, and they can approach from the backside and attack the carbon much more readily if that solvent shell isn't there, or is very weakly bound. Um, this is an example of different things that you can make uh, by reacting an alkyl halide with a nucleophile, and all of these are SN2 reactions that are shown here. So you can take an alkyl halide, you can make alcohols, you can make ethers, you can make esters, you can make nitriles, you can make alkynes. This is an important reaction because you're making a carbon-carbon bond here. You can make azides, you can make amines, you can make thiols, you can make sulfides, and there are more and more things that we're going to learn how we can make. But in all cases, these things are just behaving as the nucleophile. They all have either a lone pair of electrons or a lone pair of electrons and a negative charge. And so these are all decent nucleophiles. So you can have oxygen-containing nucleophiles, carbon-containing nucleophiles, nitrogen-containing nucleophiles, sulfur nucleophiles, and so on and so forth. And these all proceed quite easily to make these different functional groups. So you can convert alkyl halides into alcohols. If you use hydroxide, you can convert alkyl halides into ethers. You can convert alkyl halides into esters, so on and so forth. So to carry out the synthesis of a particular compound, you really have to think kind of backwards. This is known as retrosynthetic analysis. And I'm not going to spend a whole lot of time on it right now. We'll deal with it a lot more when we get into Organic 2, but we kind of need to introduce it right now. So let's suppose I sent you into the laboratory and I asked you to make 2-methyl-1-propanol, and that's all I told you. Well, what you'd have to do is you would have to look at this particular molecule and think backwards into what starting materials you would need to actually do this particular type of chemistry. And so we know right now that we can make alcohols from alkyl halides and hydroxide, for example, through an SN2 reaction. And so that's probably what I would be thinking. Okay, and so on Friday, we'll actually think about this particular reaction at the beginning of class as well as the demonstration. So again, don't forget to bring your device to class on Friday to record the demonstration that we're going to do